And thank you so much for this opportunity, and thank you, Brian. This work is very much a multidisciplinary collaboration together with Brian, Breakthrough Listen, also Andrew Simeon of Breakthrough Listen, and Ian Crawford over at the Center for Planetary Sciences at UCL Birkbeck, where I am also a research fellow. But I work as an affiliate scientist with the SETI Institute, and my focus over the last dozen years now or so has been on this notion of technosignatures at the micron and submicron scale. And as Brian has hinted, looking within our solar system to see what we may have collected and what the methods that are practical that might be for detecting and identifying them, or at least constraining the problem. As Brian said, ground into dust. There are many astroengineering opportunities possible. The decay and grinding to dust of Dyson swarms and other structures may mean that the dust that we observe and pass through in our own galaxy is a potential reservoir source intersection point for whatever is carried in it. This is picking up directly from Brian's point on probing not just distance, but also time. So just as Brian has underscored, those technosignatures that are not continually sustained, the ones we might more typically look at, limit our detection opportunities because we are not sampling them into deep time. The distances between stars are inhibitive for passive detection. So the very mirrors and lenses described are a challenge. But what we're aiming to address is this notion of the dust. The dust of other technological societies would actually have had ample opportunity to reach us from across the entire span of the Milky Way. Can't resist this when we discuss this concept of discovering what might be on the airless bodies and other points of the solar system. We, of course, think about past speculation about artifacts that might have been purposely left. And although that may be an opportunity even at the micron and submicron scale, which we will discuss, what perhaps is most energizing for this team is that it is the passive dust at the micron and submicron scale that may provide some of the widest opportunities and most important opportunities for exploration. I also recall that Carl Sagan himself, back in '63, before the first orbital surveys of the moon, was also proposing that we use those orbital surveys to look for what might be automated bases, for example, on the far side of the moon. We're looking at something much more constrained and modest. This idea that these particles might transit the galaxy goes back at least to a Ukrainian researcher, Alexei Arkhipov, back in the early 1990s. He was thinking of larger debris fragments at the sort of gram to kilogram scale. But what caught my attention was the idea that even micron-sized debris would likely be traveling for free under natural radiation pressure, stellar winds, accelerated perhaps by supernovae events. So this is what we're looking to expand on in this work. Looking at what the sources of micron-scale technosignatures might be, thinking through how they might not only arrive, but enter through the heliosphere and come to reside on natural collecting plates like the moon. My background is in meteoritics and impact studies. Wes, I appreciate you're online. I know much of your work. And recently I've been working very closely with asteroid sample teams here in Japan, where I'm based, with the JAXA asteroid Ryugu team. And to say residing on natural collecting plates may be too calm. These are actually arriving as typically hypervelocity impactors at least 2 kilometers a second, maybe exceeding 10 kilometers a second. So whatever comes in at this scale is actually going to crater, make a mess, possibly vaporize. So aside from some of the statistical challenges, which we'll address about how much dust does it take for something of interest to arrive in the solar system and on an airless body, like the moon or the asteroids, which might be ideal collection environments, there is the issue of how do you detect something that might not be there or not much of it. So we've been focusing on computer vision and AI machine learning techniques. We'll see, for example, Laura, looking at your approaches and foundation models. We have kind of gone the other direction with convolutional neural networks to sample on trained and labeled data with perhaps lower degrees of accuracy, but a higher probability of discovering anomalies. We look at also what might these particles be made of? Firstly, as mere debris, but also it is possible that such particle sizes may be attractive for storing information, for sensing, for communicating, for acting as antennae and other possible uses. So then we try to look at what are the probabilities and constraints on discovering accidental dispersals within the solar system, and also examining what the detection probabilities and constraints might be if such dispersals are intentional. Brian has addressed Dyson spheres, Dyson swarms, what happens when they break up. And echoing his slide in discussion, these are things that really don't just casually orbit. They require maintenance. If a civilization has gotten bored with its Dyson swarm or evolved beyond a need for it, or simply died and gone away, maybe before they've passed on to other stellar systems and other Dyson swarms, then without maintenance, these things will indeed grind to dust, which suggests that there may be quite a bit of mass throughout the galaxy if any such civilizations have developed such megastructures. And here exactly, as Brian discussed, analogous to orbital debris in our own planetary environment, these are producing cascades that may be providing real reservoirs of material. So we have these ground elements. They're at about the right size. A micron or less is kind of ideal for transport through the galaxy on radiation pressure. A micron and maybe a little less is just about good for passing through the heliosphere and not being pushed away by it. And depending on the impact velocity, there's a chance that we may find either the particle itself, depending on particular channels of arrival, and remnants of their own impact. There are places we might look. We've evaluated in our recent work. We're currently in submission process exactly on this work. There are pockets of the interstellar medium, hot, warm, cool, and cold. Some of them are safer for these kinds of particles and their survival. So we've been evaluating which ones are likely to provide reservoir pockets, and also evaluating how often do we as the solar system intersect these particular pockets. Once something gets here, it's also getting mixed into the surface of the moon, asteroids. Of course, these would also potentially have arrived on Earth, but Earth presents its own special problems for these size particles. When we think about, for example, micrometeorite impacts and dispersals, the combination of plate tectonics and volcanic systems and atmosphere and stuff don't make the Earth the most enviable detection environment. But it turns out, we believe, that normal mixing of the surface probably means that the upper meter or so of the moon could be an important depository. Things also we see seem to survive. Vasilevsky has done work in the past showing, so for example, this is a lunar rock from the Apollo 16 mission, the surface of which has been exposed to gardening by micrometeorite bombardment and other factors, and the lower half has been buried. And even the long exposed elements of such rocks are pretty durable. And if we think about things that have been artificially manufactured, we might anticipate that their durability over time is even better, even at the micron scale. Detection techniques. We've been developing these firstly for kind of easy targets. Each year, as part of the astrobiology project Tampopo, spores and microbes are exposed on the exterior of the International Space Station, the Kibo module. But also there are silica aerogel collecting plates to pick up things that may be in the high altitude atmosphere, but also potentially interplanetary dust or even interstellar dust particles and their tracks. So we developed a you only look once extraterrestrial algorithm to be able to identify and sort and classify. And I'm pleased to say that in the receiving lab here, we have now outperformed humans in being able to distinguish very small particles within comparatively large sample collection plates. We then extended this to the macro scale. We recently released another paper on what might be the discovery of a long-lost macro scale artifact, the Luna 9 first lander on the surface of the moon. One reason we took an interest in this is that when we think about what such micron particles might be, it is also possible that they might have been equipped intentionally to be able to use local resource, maybe even the energy of impact, to be able to begin some kind of replication or probe development process. Maybe macro scale artifacts are descendants of micron scale naturally traveling probes. So hence it's worth looking. And I appreciate that there are parallel efforts undertaken on this, looking for spacecraft hardware on the moon. But here we developed and trained the model on Apollo spacecraft, and using unseen LROC images, it is detecting artifacts that have not been detected so far by humans. This also echoes the work by Daniel Angerhausen, who is using larger, untrained, unsupervised machine learning models. We've been discussing pretty intensively on the complementariness of these approaches. And machine learning and computer vision are really becoming very powerful tools at every scale for these kinds of searches. So we've been training on the tracks, on the particles. So here we even see biological elements. And in terms of thinking about what to look for, the cratering processes themselves may have morphological differences. Therefore, we are designing and running hypervelocity gun experiments between natural and artificial particles or their surrogates to be able to see if we can train the models on the crater morphology as well as what the objects themselves might look like. We do see microcraters from micrometeorites, possible impactors, IDPs, maybe ISPs. So recent publication from a different Ryugu asteroid team examining what are pretty clear impact craters, splashes from the impactors, melts from the impactors, And under geochemical analysis, these are pretty clear iron-rich, likely cometary particles. But just to say, there is ample material for us to begin further model training and deployment. And indeed, microcraters and structures on the moon. Here from the Chang'e 6 return samples, there are characteristically large numbers of interesting structures that reflect impactors from micrometeoroids and IDPs, potentially ISPs. And again, training on these resources may provide us the kind of volume capability to meet the statistics. Recent experiments we've been running these are just, we grind up Earth spacecraft and then seed them over lunar simulant to train the model to be able to pick out elements. These are at larger scale, but we're moving down in the scale to get to the micron and submicron level. This is a useful tool. For example, here's work we're doing correlating asteroid Ryugu to unmelted micrometeorites in the transantarctic mountain suite. Again, we think this becomes a powerful tool for these kinds of examinations. And then to think about what might we be looking at and for. I mean, here on Earth, we're doing some pretty incredible things. The scale bar here is about 5 microns. This is a microscopic geared meta machine. It uses incident light to do nanoscale operations. These things are getting smaller and smaller. So debris may not be simple fragments of alloys, but actually they could be micro machines that were developed for other purposes, deployed in large numbers as part of large astroengineering exercises. And if they even partially survive their arrival and impact, would certainly stand out as being of great potential interest. We shouldn't rule out the biological. Over at the SETI Institute, I've been enjoying quite a few discussions with David Deemer, an astrobiologist who is focused on self-replication processes in RNA without enzyme template. So looking at, could RNA or equivalent have arrived at the early Earth and begun its own self-replication process? He is suggesting hybridized biological and mechanical micron-scale capabilities, bearing in mind that bacteria itself, DNA, is also micron-scale. So if you can make these things robust enough, maybe strip out genetic code and put in a machine code, it is possible that we might have some form of information or intelligence embodied even at the smallest scale. There has been some work done by Sophia Sheik on the practicality of solar system SETI. It's been a chart that's been used many times. And we've kind of modified this in our recent work to look at the benefits, the sheer potential abundance, and being able to look here in our neighborhood at the small scale particle, we believe is an attractive endeavor. Finally, and this will appear in our recent work, we believe that even relatively small volumes, like the approximate volume of lunar materials that have already been returned to Earth, is enough to begin to constrain the problem. If we go back to Brian's assumptions about longevity and replication, we can begin to think about the equivalent of every solar-like star in the solar system, in the galaxy, being a potential source over time. And even looking at a small volume of the moon at what used to be pure needle in a haystack, but which is now soluble using computer vision and machine learning, we can look at trillions of particles in small volumes and begin to constrain potentially the number of past technological civilizations in our galaxy. Thank you.